I feel like if I go over it, it'll help a little bit. So, I'm going to go quickly through this, and I'm going to slow down for the rest of it, okay? So, you know that in special relativity, anything in 3D must become a four-dimensional object, right? That's sort of one of the key things in building the special theory of relativity, starting with Galilean relativity. Galilean relativity is based on three-dimensional things, and then you have to promote like a three-dimensional position vector to a three-dimensional space-time vector. So, for example, you know, you talk about dr. Why are none of these working? Jesus. And then to relativize this, God almighty, I bought a whole box of these things and none of them are working. This is crazy. This becomes, oh my God.
Alex.
What? Okay, wait, this is the one that's, yeah, this is the one that sucks. So, and I'll just do the whole damn lecture with this juicy bit. Okay, no, seriously. So you know that everything that's three-dimensional has to be enhanced to a four-dimensional thing. And so that immediately poses an interesting question. In electricity and magnetism, we have these 3D vectors, E and B. So if we want to special relativize electromagnetism, which you don't really have to do because electromagnetism is already relativistically invariant, but if you want to write it in the four-dimensional language of special relativity, what do? I mean, these are EX, EY, EZ, BX, BY, BZ. What the hell do you put in for the time component? Well, it turns out there's two different ways that you can handle it. First of all, you can forget about turning this three-dimensional vector into a four-dimensional vector, and this three-dimensional vector into a four-dimensional vector, and just lump them into a two-dimensional tensor, okay? So one way to approach it is instead to build a 0-2 tensor, which is built out of all of their components. Okay? It's an anti-symmetric tensor. If you interchange mu and nu, then you should get opposite what you started with. And you can recognize that's reflected by an anti-symmetric matrix, which of course must have zeros on the diagonal. Because if you had something non-zero on the diagonal, there's no way you could have this be true. So if you think about it, a 4x4 matrix with zeros on the diagonal needs 1, 2, 3, 4, 5, 6, 12 spots filled, but only 6, because if you have 6, you automatically have the other 6. And that's what the 6 components of these are put into, okay? So that's one method of doing it. It turns out there's another method of doing it. Which is to say, okay, well, remember that the electric field you can build from the gradient of a scalar field plus the time derivative of a vector field. And the magnetic field you can get from the curl of a vector field. So if I actually just forget about E and B for a minute, I have a vector with 3 components and a scalar. What do you think? How about A mu equals the scalar potential for its time-like component and the vector potential for its space-like components? Seems like it'd work, right? Okay? Now, you know how this would transform under a Lorentz transformation, and you know how this would transform under a Lorentz transformation. Turns out these two approaches are the same thing. The only thing you have to realize is that F mu nu is defined in this way. Okay? So there's a little bit of work that goes into forming this from this. You've got to turn this into its dual vector, so the phi gets a minus sign. And then you're going to make an anti-symmetric combination of derivatives. The anti-symmetry is obvious in this definition. This property is obvious here, because if you reverse mu and nu, then this term becomes this term, and this term becomes this term, and so the minus sign is just an overall minus sign. Okay? So, for example, just to show you how this works, if you want to calculate the component of F01, then you would say, okay, I got to do D0 of A1 minus D1 of A0. And we can find well, we've got a mu dual. Okay? So then this is 1 over c times the derivative of ax with respect to time minus d phi dx. Remember, this is d0, so d0 is 1 over c d by dt. d1 is d by dx. d2 is d by dy, etc. So the d0 is 1 over c d by dt. d1 is d by dx. a0 is phi, negative phi. Did I do that? Oh, sorry. A mu should be negative phi, and then a dual should be phi. Sorry about that. I didn't see this in my paper. Anyway, this is what it works out to be. But that's just, if you compare it with this expression, that's just minus e sub x. Okay? But that's exactly what we expect in the F01 spot. Okay? Am I on board with that? Okay, I just bring this up because F mu nu is going to appear later in the course. Okay, we're going to do the underpinnings of QED, quantum electrodynamics, and F mu nu plays a very important role. And there's another example of one, F23, on the notes, but I'm not going to write it on the board. Yeah?
If this is too long of a question, I can ask you after class.
Go for it.
But so we wrote down F mu nu, and I've always just wondered, how do you pick where the negatives are and like where you place the E and B components? Because I know it's anti-symmetric, but like how do you pick where they go?
Oh.
Sure, yeah.
What was it like from?
That is.
I don't remember.
It's in the textbook.
What?
Well, it's in the E&M textbook.
Yeah.
Yeah, the E&M textbook sucks. No, because honestly, this notation is shit. Okay? Because I would ask you, all right, fine. What if you're doing 5-dimensional relativity? What would you do? Well, you'd say 0 minus EX minus EY minus EZ minus EW. Okay? And these are easy. And then we got zeros down the diagonal. Okay? And then we've got 1, 2, 3, 4, 5, 6 things we have to fill in with magnetic fields.
So it only works for evens, right?
It only works for what?
Even dimensions? Or something like that?
It only works for 4 dimensions.
Or just 4 dimensions? Ew, that's sad.
No, it works for any number of dimensions.
So do we just put more zeros?
No, it's just that, look, this is the same horrible thing that we do. I mean, I've been doing it, but this is the same horrible thing that they do in E&M textbooks. They treat B like a goddamn vector. It's not a vector. B should be associated with planes.
Oh, okay.
And then you know there are 6 planes when you're living in 4 spatial dimensions. Okay? So, yeah, I mean, so this is actually going to be our fundamental derivation. And this applies in any number of dimensions. So this is what I would hang on to and not worry about, let's write down the matrix. How does the matrix change if you're, yeah.
Thank you.
Okay? Any other questions? Yeah.
Well, this might seem a little bit dumb, but since B is a pseudovector, then does that mean that if you were to like apply a parity transformation in 3 dimensions to F mu nu, then would the signs on all the B's change?
No, they wouldn't. No, they wouldn't. They would change on the, if you do a parity transformation?
Yeah.
No, if you do a parity transformation, the signs on the E will change, but the signs on the B won't change.
But no, but in F mu, but what I'm saying is that F mu nu, the sign, is since F mu is a tensor, then its sign will change. So, but then will be signs of the B's in F.
Yeah, I'll think about that later. I got to go on to today's material though, now, because I'm already almost 15 minutes in.
Sorry.
No, it's fine, it's fine. You should ask me that question when you're in my office though, Ross, because it's a good question. I just have to process it. All right. Okay. So now, now I'm getting nervous. 'Cause now we're getting into the good shit. Okay. So, and it's funny because I'm going to give you the same example I've given the last 2 or 3 times I've taught this course, but it's a goddamn good example, so I'm going to give it to you. So quite often in physics especially, because you're not mathematicians. Oh, sorry, you're a mathematician. But in physics, you define things in concrete physical terms, okay? And that's a very intuitive way to do things. But you will find if you allow yourself to provide a mathematical definition of something and sort of throw away your physical starting point, the mathematical definition often is much richer than just your physical definition. Now you might realize that that's just leading into playgrounds for mathematicians to, dance around and do stuff that has nothing to do with the physical world. But on occasion, we've taken physical starting points, abstracted them mathematically, found a larger neighborhood of stuff that math can describe, and then discovered it physically. And we're going to talk about an example of that in our next meeting, but we're going to build up the background structure for it today. Okay? So what do I mean by a concrete definition? So for example, let's take this mathematical object, cosine of theta. As a physicist, if you want to define this, what you'd say is, well, I know what you do. You go out and you build a goddamn right triangle where theta is one of them frickin' angles. Okay? And then you measure this thing with a ruler. You measure this thing with a laser. No, with a ruler too. Okay? And then you take the division of the L over the H, and that will define the cosine of that angle theta for you. Everybody on board?
Yeah.
Okay? We good? Yep. Did I get that right? Because I'm nervous. Is that right?
Yeah.
Okay, good. Because my memory is gone, man. Sine theta, cosine theta, the same thing. Aren't they? I don't know. Anyway, okay, but this could be your sweet-ass definition of cosine theta. But then I walk up to you and I say, oh, that's good. What's that? And I know what you'd say. You'd say, I'd build a right triangle. They had an imaginary length. Had a real length. And that's it. That's the answer. Shut up. Okay, this doesn't work. This doesn't work. Okay? So, we need another definition of cosine theta. Not in terms of triangles. This is, of course, the first place you ever met a cosine theta was when you were doing trigonometry as a kid. Now, this is not the only way to define it, but this is just an example. What if we instead what if we instead define cosine theta, or I've got x in my notes, so I'm going to write x just so that I actually do this. What if we define it by its Taylor series? Okay? Now this is definitely not triangle related. This is an infinite series. You know, if the x is small, you can use the first two terms to approximate it, da 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 da. Well, I mean, if you hand me a triangle with an angle in it, theta, and I want to evaluate this with theta, then that's easy. I just plug theta in. And I do all infinite terms, add them together, and god damn it, I got the value of cosine theta. However, if you handed me I times theta, and by the way, I hope you all know that I here is the square root of -1. But if you hand me I theta, then, well, shit, I can plug in I theta into this Taylor expansion. This makes sense. I squared is -1, I to the 4th is +1. I can evaluate all infinite terms, and this will let me give you the value of cosine I theta. So this is just an anecdote of the story of sometimes it's useful to get away from your physical definition of mathematical concepts. Allow yourself a more abstract definition, and you might find that that abstract definition applies to more cases. Okay? And by the way, it's only this definition which would ever help you find such beautiful connections as, of course, the connection between the function cos theta and cosine theta. Okay? So, this is just a sort of an example, a play example. Now I want to actually touch base on what we're doing and how we're going to generalize something to a more vague mathematical definition, which is going to let us apply it to more situations. All right. Oh, don't ever get old, I tell you. It sucks. Okay. So, for our discussion, rotations and Lorentz transformations. Okay, I'm going to pick on those. That's going to be the real meat of this subject. Has been heavily focused on concrete representations like coordinates. So, for example, you know, dx mu goes to dx mu prime, which is lambda mu prime mu dx mu, where dx mu is concretely a vector made of coordinate differentials, okay? Coordinatizing geometry, that's very physical. It's got a very physical basis. You know, I mean, you put down coordinates, but the coordinates stick in the room. You know, the room is here, the room is physical. Okay? With this basic starting point, though, with this basic starting point, figuring out what these lambdas are, we can then build dual vectors, tensors in general, okay? So we can get a lot of mileage out of this that is way more complex. It's all rooted, though, in this basic definition of these transformations in terms of coordinatizing a space. That's a very physical starting point, okay? We want to get away from that. Now, there's something really interesting about the answer to how to do this, and that is that, remember back when we were talking about multiplication tables? Remember those? And I said, hey, actually I had 3 guys come up to the front. It's pretty sweet. But if I do the multiplication table of +1 and -1, I get +1, -1, -1, +1. And then if I do the addition of even and odd numbers, I get even, I get odd, I get odd, and I get even. And we said, you know what? Those are the same damn underlying group. Because they have the same multiplication table. Okay? And I told you, this is a mechanism for comparing 2 discrete finite groups. Okay, they got to be discrete so that you can actually put the elements into these individual blocks, and they got to be finite, otherwise it's an infinite matrix. You know, you don't want to do that. But if you have a discrete finite group, or two of them, and you create their multiplication tables, and their multiplication tables are the same, then you can say the underlying group structure is the same. And then I said, however, if you have a continuous group, you're screwed. Because continuous groups have an infinite number of elements. Okay? However, what we're going to talk about is going to provide us a manner of comparing two continuous groups and asking, are they actually the same group or not? Okay? You'll see how that happens later on, but it's just sort of a huge plus that comes out of this redefinition. Okay. Now, one of the key things to recall is for example, SO3. We'll pick on SO3 for a bit. SO3, how many elements does SO3 have? An infinite number, thank you, because it's parameterized by 3 angles, and those angles take continuous range of values. Okay, it's not an infinite range of values, but it's continuous, so it's an infinite number of transformations. However, and this is a key thinking point, however, I can kind of take any rotation and I can kind of decompose it into a rotation in X, a rotation, well actually let's say it correctly, a rotation in the XY plane, a rotation in the YZ plane, and a rotation in the ZX plane. So I can somehow break this down into, somehow these are the fundamental rotations, and to make a big rotation, you just do a lot of rotation in XY. Or a lot of rotation in YZ, or a lot of rotation in ZX. Okay? Okay, so I'm going to do a quick brainstorm before we actually push into the answer. And my brainstorm is thinking of things which describe groups. I gave you a whole laundry list of words at the beginning of the semester, and we've talked about more words since then. If I wanted to compare two groups that are continuous and figure out if they have any hope of being the same, what properties would you expect that the two groups would share? So for example, do you think that the two groups would share the same number of free parameters? Do you think I could have a group which has one free parameter and a group which has 3 free parameters somehow be equivalent? No. So that's got to be the same. What about abelian versus non-abelian? Do you think if I have a group which is non-abelian and a group which is abelian, I can somehow prove that they're the same group? No, it's got to be the same. Dimensionality of matrices that form representations of the group. If one of them has a 4x4 representation, the other one has a 16x16 representation, could they be representations of the same group? Yeah, you should have learned that from your homework. In your first assignment, you did an 8-dimensional represent, then you did a 1-dimensional represent of the same damn group. So no, you don't require this. Okay? Here's an interesting one. If I have a group which is represented by, say, real matrices, and a group which is represented by complex matrices, do you think there's any way those two groups could be the same?
Yeah.
Yeah, they can be. So this is not required either. Okay? And you could go through other words describing groups and decide, but let's actually dig into the details of it. All right. So fortunately for us, in this class, almost every single group that we are going to deal with, and I'll just list the ones that we're going to deal with. There's our space-time group, there is our group governing the strong interactions, our group governing a part of the weak interactions, and our group governing electromagnetism, although these are going to get a little intertwined. As well as you can talk about rotations, but these are the four main groups we're going to deal with. These are all examples of a particular group structure which is hugely beneficial. These are all Lie groups. Now, that's Lie, not lie. So you heard me say it right once. Don't talk about Lie groups. But anyway, Lie groups. Lie groups are always going to be continuous groups, but they're going to do something really cool. A Lie group is actually going to form a differentiable manifold. So what I mean by that is, if I take one transformation in a Lie group, and then I take the next transformation in a Lie group, and the next transformation, and they might form a line, which happens to be infinite. So that's a differentiable manifold. You can put functions on it, and the functions are well differentiated. Okay. But then a lot of them also form planes. Some of them form spheres. Okay. Now, a very interesting part of this story is that for a Lie group, if we can figure things out how they behave infinitesimally, then we can almost form the entire group. So, let me go back to an example that I've already given you. If you want to talk about rotations in 3 dimensions, so that's a 3. Then if you happen to know, actually let's just do SO2, rotations in 1 dimension. So I have an XY coordinate system. If you know how to do a rotation by 1 degree, that's a small rotation, right? And the beauty is that if you know how to do a rotation by 1 degree, then you automatically know how to do a rotation by 45 degrees. Right? What's a rotation by 45 degrees? It's a rotation by 1 degree raised to the 45th power. It's pretty sweet, isn't it? And then you can do, you could do 90 degrees. Okay? But this is not super useful, right? Because what if you wanted to do a rotation by 260.3 degrees? I can't do a 0.3 degree rotation if I'm only building with integer blocks of rotation. Okay? However, if we could somehow write down the rotation in the xy plane with an infinitesimal angle, if we could somehow write down the form of that, where this can be taken arbitrarily small, then we've got the building block we need. But the question is, how does this work? Okay? And we're going to answer that. That's the beauty of Lie groups. They have an answer to that. The beauty of Lie groups is if you can give me a transformation over a very, very tiny parameter, then I'm going to give you a map where you can compound these and create an arbitrarily large transformation. Yes?
Why can't you almost form the entire group? You put an almost on there. This doesn't seem like it has
I'm going to talk to you about that the next time we meet.
Okay.
I can't possibly describe it to you right now.
Okay.
Well, I can put it in these words. So what you're doing, no. So here's the answer, but it will make more sense later. So your group forms, these groups form a manifold. So, I mean, maybe they form, maybe it forms a circle. No. Maybe it forms a, maybe it forms.
Is this just like a manifold? Fine.
Okay, so it forms the surface of a torus. Okay, now that means that if you pick any point on the surface of this torus, that corresponds to an element of the group. And you can obviously pick 2 points which are arbitrarily close together. Okay, so this is a continuous set of group elements. Now, what we're going to do is we're going to pick an origin, say there, and we're only going to be interested in finding the group elements an infinitesimal distance away from the origin. Okay? And then we're going to have a map which lets us compound these to create non-tiny things. Okay? However, this thing might be part of a torus, or it could be part of an infinite two-dimensional plane. Because this is flat, and this is flat. I know you don't want to agree that a torus has a flat geometry, but trust me, it does. A torus has a flat geometry. This is a flat geometry. The geometry is local to the origin, and both of these cases are the same. So really, if all you know is what's around the origin, you can't tell about the topology of the overall group structure. And we're going to see a very concrete example of two groups which have the same infinitesimal structure, but they have very different topological structures. Okay, and we're going to talk a whole lecture about that. Okay. All right. So, any other questions?
Did we dare ask?
Yeah, no, don't. Okay, so here we go. So I'm going to formalize this.
You could ask very loaded questions if you were in GR.
Well, no, I'm running out of time. I got to get through these 2 pages, and then you can ask me questions at the end if we have extra time. How about that?
You used to run like 15 minutes over every class.
I know, and I'm trying not to do this. I'm losing them one at a time. Okay, so here we go. A group element, this is not an infinitesimal element, this is an arbitrary element. A group element of a Lie group can be written, and by the way, those who took GR, welcome to, because this shit ain't covered in GR at all, can be written as the following. A equals e to the I g a v a, where GA is said to generate, that's why I put a silencer on you, generate A, and VA is a vector of parameters.
Why is it said to generate? That seems like
It's not, it's said to generate, because, well, okay, fine.
What? Okay.
This is going to define a word for us that we're going to use extensively, though, so I wanted to pick it out.
Why are there so many A's
Huh?
in that top expression?
A group element of Why are there so many A's here? Well, I mean, I guess I could call this. Well, I have A in my notes. That's why it's there. I mean, you could call it A. You could call it G. You call it whatever you
So
want.
like all the eight, that's not like super
not the same
meta,
eight.
like tensors within tensors or some garbage.
No. I'm going to explain this. I just threw something up there and we're going to break this thing apart. Yes, go ahead.
When you say GA says to generate, do you mean it's a generator or is it something?
Yes. These are called the generators. Okay? So a couple of important notes. If G is an n by n matrix, okay, so if you want to represent your element of the group by an n by n matrix, then you have to use an n by n generator. Okay? So, I mean, this is an exponential map. I'll talk about this in detail in a minute, but I just want to point out, these two things are going to be matrices generally. They could be one by one matrices, but these two are matrices and they have the same dimensionality. Okay? Second point. The combination of GAVA allows us to combine transformations. So for example, if I want to talk about doing a rotation in 3 dimensions, but I want my rotation to include a rotation in the xy, a rotation in the yz, and a rotation in the zx all together, then I would take something like that. So this is an inner product of the vector of generators and the vector of parameters. Okay? And this is just based on how many generators we have in our group, which is going to be directly reflective of how many free parameters we have in our group, by the way. Okay? And so, again, if I want to do just a rotation element in the xy plane, then this is just I e to the ig xy theta. And I'm basically taking phi and psi to be 0. But I don't have to do that. I can do something which is a combination of all of these. Okay? I mean, think about it. This is a group. I could take a rotation in the xy, a rotation in the yz, a rotation in the zx, combine them all at once, and they would have to give me another element of the group. And so this is giving me one expression to define some composite thing like that. I just fill in all the different angles. Okay? All right. Any? Yeah.
Dumb question time.
Yeah.
So addition commutes, right?
Addition commutes.
Yeah.
Yeah, I know what you're going to talk
Yeah.
about. Don't worry about it. I am not going to lay that on you in this class.
Okay.
Yes. So we are going to, fortunately, mostly focus on single parameters.
Okay.
But yeah, in the exponential, you've got a matrix and an exponential, and we're going to even address that slightly in a minute. But yeah, if you've got an exponential of matrices, then you got to be really careful in how they break down because things don't commute. So yeah, I agree with you. But I'm not going to throw any of that on you in this semester. Okay? I don't think, but we'll figure it out. Okay. So, let's see. So if I were to do a rotation in the YZ plane, and I know I'm writing this down, and it's reflective of what I've got, but I just want to have what's in my notes. Then I would do e to the I, the generator of a rotation in the YZ plane, times some angle theta. I'm using the angle theta for the YZ plane. So, first question. I got a matrix and an exponential. What the hell do I do with that? Hey, Ross. Okay, anyway. Yeah.
see these?
Yes, exactly. Yeah, if you don't know how to exponentiate a matrix, Taylor expand that son of a bitch. Okay, because if you Taylor expand this, then you know you got the identity matrix, and then you've got I, G, R, Y, Z times theta, and you got minus 1 over 2 factorial, G squared, R, Y, Z, theta squared, and I'm going to go ahead and write one more term for obvious reasons in just a minute. Okay, now if I say, oh, that's a matrix, what do you do? You're fine, because this is a matrix of the same dimensionality, this is a matrix of the same dimensionality, and this is therefore the identity matrix of this dimensionality. This entire right-hand side makes total sense. Okay? And the dimensionality of this should also be the dimensionality of this, as I pointed out here. All right? We good? Oh, man. Let's pretend I didn't show this.
It's too late now.
I gotta do it. It's in my notes. I gotta do it. Oh, man.
You are not a slave to
An exponential of a matrix.
What's that floor noise?
Exactly. Thank you. All right, anyway, this sucks. God dang. I forgot to write down what's in my face. Anyway, that's an old joke that I use in every class. I'll use it again in this class, but when I write WTF, I mean, what's that for? Like, anyway, shut up. Okay, so here's what I'm going to do. We got a place we got to get. Okay, so now what I'm going to do is I'm going to unpack this, because I would like to know what the hell that is. I mean, I said it's a matrix. Look, you know what this is? This is the 3x3 identity. You know what that is, hopefully. You know what that is. That's whatever angle you're going to rotate by. But what the hell is this? And then what is that? And then what is that? Oh my God, there's an infinite number of them. Okay, but still, if you could just give me that, at least I could in principle calculate those. Okay, I'm going to dig out what G, R, Y, Z is. So in order to do that, what we would say is, if I want to rotate a vector, then my rotation matrix, I know, would look like the following. I know what this thing right here would look like. This would look like 1, 0, 0, 0, 0, cosine theta, sine theta, minus sine theta, cosine theta. Okay? Now I want to equate that to a Taylor expansion. So why don't I come in here and Taylor expand all the little bits? Yeah, let's do it. So if I Taylor expand this, then I'm basically just Taylor expanding cosine. I mean, I'm Taylor expanding 1. Taylor expansion of 1 is? Taylor expansion of 0 is? Nice, you guys are good. I'll do the hard ones. Okay? So obviously the Taylor expansions are infinite. Okay? But there you go. There are my Taylor expansions. Wait a minute. Hold on. What's down the 1, 1, 1? Oh, snap! Boom! Okay. Theta sits here and here. So I have to have a matrix which multiplied by I and theta give me this and this. What matrix do you think that is? That's GRYZ. Okay? So we can immediately extract GRYZ from this. It's going to be 0, 0, 0, 0, 0, minus I, 0, I, 0. You can get it just by looking at the theta term. Turns out it works for the theta squared term as well. Okay? Does everybody understand how I got this by just looking at what I need to get linearly in theta? I mean, let's do it. Damn. I theta times g ryz is 0, 0, 0, 0, 0. I times minus I is 1. So this is theta. 0 minus theta, 0. Minus theta is what I need there. Theta is what I need there. It did it. Of course, this term is going to give me the theta squareds. This term, okay. So I just got the form of the generator. Now, you might say, well, this is the cool thing about generators. If I square this generator, I get 0, 0, 0, 0, 1, 0, 0, 0, 1. So if I cube it, I get the original generator back. Because this is just acting like an identity on the space where things are non-trivial in the generator land. Oh, wait a minute. That means that you can actually evaluate this. Because all the generators are going to come out. You're either going to have factors with a GRYZ or a GRYZ, sorry, this is squared. You're either going to have GRYZ or GRYZ squared. If you take all the terms that have a GRYZ, and then you take all the terms that have a GRYZ squared, you can then re-collapse all of the sums into sine and cosine. Okay? So you can demonstrate that this actually reproduces the entirety of this summation. All right, it's pretty cool. Okay. Now, if we're going to talk about rotations, then clearly we have three generators to be concerned with. We have xy, we have yz, and we have zx. And you're going to have different matrices for them, so I'll just write down what they are. So let me see, GRZX is 0, 0, I, 0, 0, 0, minus I, 0, 0. And GRXY is 0, minus I, 0, 0. Okay? Now you might ask yourself, are these the only set of three matrices that you can use to generate rotations in 3 dimensions? And the answer is, hell no. Okay? You can actually change the form of all three of these, but they've got to be kind of tied together in the right way. But all you're doing when you want to transform these is you're doing a rotation. It's not obvious how you would rotate these, but if you do an underlying rotation of the 3 x, y, and z axes that you pick to start with, it will transform these. So they'll change, but they'll still work out in totality. Yeah, go ahead.
Why does the ZX one have like the negative in the different spot? Because you think you'd build it out of sort of just rearranging the sines and cosines, so it's not.
Yeah, I mean, you could.
It just happens
Yeah.
to work like that? Okay. Just like that.
Okay. So now these generators, I want to, the generators are these 3x3 matrices. Like, is this a rotation? No, this is not a rotation. A rotation you get by exponentiating a generator with an I to the I and an angle, okay? Even though this is a 3x3 matrix and this is a 3x3 matrix. Go ahead.
You said VA is a vector of parameters, but theta we use theta as a scalar, right?
Yeah. So VA in this case is this vector.
Okay.
And yeah, so this is the reason I said that, because if you can rotate your GAs, you need to be able to rotate the vector of parameters as well so that this thing is invariant. Okay, but that's a bit technical, and we're not going to mess with that in this class, but yeah, that's true. Okay, so I gotta put the cream on the crop here, because this is not the end of the story. This is only the beginning. Now we're going to take it where it needs to go. You might have noticed that everything that I just wrote down was highly coordinate dependent. I mean, I was talking about rotations in 3 dimensions. Everything was represented by 3 by 3 matrices. I built the generators from this rotation matrix. Like, that's all very intimately tied to the damn coordinates. And I said, we're going to get away from physical things. We're going to get away from physical beginnings. Well, let's see if we can do that. I want you to consider the algebra of the generators. And when I say the word algebra, what I have in mind is you take the commutator of 2 generators, doesn't matter which 2, I'm just picking these 2. Who doesn't know what a commutator is? If you don't know, raise your hand and I'll explain it. Okay, if I have a commutator of 2 things, that just means I multiply them and then I reverse the order that I multiply them and I subtract. Okay? So if I take the commutator of 2 different generators, what's the commutator of a generator with itself?
0.
It's 0 because, A times A minus A times A is automatically 0. If I take the commutator of 2 generators, I had actually written out the definition of the commutator in my notes. Anyway, I don't have to do it now. For SO3, it turns out that this is just I, G, R, X, Y. Okay, if I do G, R, Y, Z, G, R, Z, X, this gives me I, G, R, X, Y. Now that's just one example of a commutator. However, if you play around with doing the commutator of different pairs of these generators, what you will uncover is the following. If you let I, J, and K take the values 1, 2, and 3, then GI, GJ is I, epsilon IJK, GK. Where the values 1, 2, and 3 are just picking one of these 3 rotations. I mean, we've only got 3 rotations in SO3, and so if I could call this the 1, the 2, and the 3 if you want. Doesn't matter. Okay? Now, for those of you who are not familiar with Levi-Civita, it takes the following values. If you do a cyclic permutation of the indices, then you get +1. That's starting with this being +1, and then any cyclic permutation of the indices is also going to give you +1. If you just interchange 2, or you do an anti-cyclic permutation, then you get -1. And if you repeat any 2 indices in the Levi-Civita symbol, then you get 0. So epsilon 1, 1, 2 is automatically 0. So all of these have to be different, and so you could just have the cyclic group and the anti-cyclic group. So for example, if I do G1 or G1, comma G3, this is going to be I epsilon 1, 3, K, or sorry, that's a 1, 3, K, GK. Well, what value can K have?
2.
It can be 2. It can't be anything else because if it's 1 or 3, it's automatically 0. So this is I epsilon 1, 3, 2, G2, which is negative. Make sense? Okay. Here's the thing. What if I took this as the definition of the group? Instead of starting with 3 by 3 matrices, what if I just took this algebra as my definition of the group? This contains information about how to find the generators. You solve this algebra for the generators, and once you have the generators, you know you can build an arbitrary group element by exponentiating the generators. So the generators are kind of the seed of love. Once you've got them, you've got everything, almost. So maybe we can take this to define our group. And here's something interesting. What if I take 2 different continuous groups? 2 different continuous groups. And work out their Lie algebras, and their Lie algebras end up being the same. That is a good motivation to say those are the same group. Almost. I keep saying almost, and we'll see the one exceptional case, but there's many. But we'll see what an important exceptional case next time. Okay? So there you go. There is a mathematical, abstractly mathematical definition of a set of transformations. It's in terms of a Lie algebra, not in terms of a matrix that rotates coordinates. Okay? We're going to use this as our definition. And we are going to find next time that there are solutions to this which are not 3 by 3. Can anybody guess what dimensionality they are? They're 2 by 2. And those represent? They represent spinors. But we'll talk about that next time. That's it for today.
In this chair.
Make sure you got your quiz from last week. Yeah, there's a pile over there, so make sure you collect those.